Hey everyone, welcome to today's Explainer. I am so pumped to have you here because we're about to dive into the truly fascinating physics of sound waves. Have you ever stopped to wonder what exactly is happening in that split second between someone speaking and you actually hearing their words? Well, today, we're going to break down that invisible architecture. We'll look at the fundamental rules that govern everything from a simple hand clap to a massive earth-shaking seismic event. But first, picture this. Let's say you and I hop into a spaceship and travel way out past the atmosphere, right into the vacuum of space. If we stepped outside in our spacesuits and I turned to you and shouted at the absolute top of my lungs, could you hear me? Could my voice actually travel through that vast, empty vacuum? Keep that paradox in the back of your mind, because the answer is hidden in the very mechanics of how sound works. All right, so here is our roadmap for today. We're heading 5 key stops. 1. What is sound? 2. Vacuum and medium. 3. Compression and rarefaction. 4. Types of waves. And finally, 5. Graphical representation. Let's jump right into part 1. What actually is sound? When we define sound as a mechanical disturbance, something really crucial stands out. When I speak to you, the physical air particles from my mouth aren't flying across the room and going into your ear. That's just not how it works. Instead, my vocal cords vibrate, and that transfers energy to the air molecules right next to them. Then those molecules bump into their neighbors, and those bump into their neighbors, creating this incredible domino effect. It's just a continuous transfer of energy passing along a chain of adjacent molecules. So let's move to part 2, vacuum and medium. To understand this, imagine a sealed, dark glass bell jar with an electric bell ringing inside of it. As long as the jar is full of air, you can hear that bell ringing loud and clear. But if we attach a vacuum pump and start draining the air out, something wild happens. As the air particles disappear, the sound just completely fades away into total silence. And the crazy part? You can still physically see the bell's hammer striking away. This brilliantly shows us that without a material medium, whether that's a solid, a liquid, or a gas, sound literally vanishes. So the golden rule here is that sound absolutely requires a medium to travel. It cannot exist in a vacuum. And hey, this is exactly why you couldn't hear me shouting in the vacuum of outer space. Out there are no air molecules to bump into each other. There's no domino effect. No medium, no sound. It's that simple. All right, part 3, compression and rarefaction. Let's zoom way in on those molecules. Think of a simple syringe or a piston. If you suddenly push that piston forward, the air molecules right in front of it get slammed together. This creates a high-density zone that we call compression. It's kind of like being on a crowded city bus. If the driver suddenly slams on the brakes, everyone standing up lurches forward and bumps into each other. That cluster of tightly packed people is your compression, and they transfer that forward momentum right down the aisle. Now, on the flip side, when that piston is quickly pulled back, it leaves behind an empty space. The molecules naturally spread out to fill that new void, causing a zone of really low air density. We call this a rarefaction. So as a sound source keeps vibrating, it's rapidly alternating between pushing and pulling, which creates this ongoing pulse of high-density compressions and low-density rarefactions radiating outward. And this brings us to a really vital concept: oscillation. Remember, the particles themselves don't travel with the wave. They just oscillate. They move slightly forward during a compression and slightly backward during a rarefaction, always returning to their original mean position. It's exactly like doing the wave at a massive football stadium. You just stand up and sit down in your own seat. You don't run a lap around the stadium, but the visual wave travels the entire length of the arena. Moving on to part 4, types of waves. We categorize sound as a longitudinal wave. That means the particles vibrate left and right, completely parallel to the path the wave is traveling, just like if you were pushing and pulling a slinky flat on a table. But compare that to transverse waves, where particles vibrate perpendicularly. Think of someone aggressively flicking a heavy rope up and down. The wave peaks travel forward toward the wall, but the actual rope is only moving up and down. Now, what's genuinely amazing is how these exact wave behaviors help geologists peer inside our planet. During an earthquake, the Earth releases both longitudinal waves, known as P waves, and transverse waves, known as S waves. P waves can power through solids, liquids, and gases. But S waves? Being transverse, they physically cannot travel through liquids. Decades ago, scientists noticed that S waves from earthquakes never made it straight through to the other side of the planet. And by tracking that missing data, they made this stunning discovery that Earth's outer core is actually liquid. How cool is that? Finally, let's wrap up with part 5, graphical representation. So, how do we take all these invisible molecular collisions and put them into a standard textbook graph? What we usually plot air density against distance, but here's a huge point of confusion I want to clear up right now. That flat horizontal line right in the middle of the graph, it is not zero. It actually represents the average, relaxed, undisturbed density of the room before any sound was ever made. Watch how it builds. When we graph it out, a high-density compression, where all those molecules are slammed together, is drawn as a peak way above the baseline. We call this peak a crest. Then, the moment of lowest density, the rarefaction, where everything is spread far apart, dips down below the baseline, into a valley. We call that a trough. So a sleek sine wave gracefully sweeping up to a crest and down to a trough is just perfectly tracking the real-time pressure changes in the air. This visual curve also gives us a fantastic way to measure the wave itself. We define wavelength, which is usually represented by the Greek letter lambda, as the exact physical distance a wave travels before its entire pattern repeats. And the easiest way to measure this on a graph is simply to take the distance between 2 consecutive crests or 2 consecutive troughs. So, we've firmly established that mechanical waves, like sound, live and die by their medium. They absolutely positively cannot exist in a vacuum because there's simply nothing there to compress or rarefy. But I want to leave you with a provocative thought. If that is the absolute unbreakable rule for mechanical waves, then how exactly does sunlight manage to travel 150 million kilometers through the complete vacuum of outer space just to reach Earth? What kind of rule-breaking wave is light? I really hope this explainer has sparked your curiosity to see just how deep the physics of the universe can go. Keep questioning everything, and thank you so much for learning with me today.